actually provide you with information with regard to the changes that have happened within the model as a result of this characteristic. And we're going to talk about a special use case version of the cross-validation methodology, and that may help elucidate some of this. But I wanted to point that out, that there's a weird aspect to this, though it is considered to be a very common methodology with respect to how we're dealing with the data sets. It's not, in fact, the real way in which you train the system. Make that clear again. I'm always going to train the model on as much of the training data as I possibly can. However, since I don't know what could happen, right, possible reconfigurations of the system, let's say that fold 4 includes the best of the examples, right? It includes the highest entropy representation, the most variance. It captures the most informational characteristics that model can have. And that fold 4 is a really well-behaved set, right? Or at least it works as well as it can with respect to it being an internal testing, internal validation process. I will then evaluate split 4 relative to all the other splits, and if that happens to come back, what's going to happen here is if this is the best representationally, it's also going to be the best from a performance perspective with respect to that degree of flexibility. But what we're also going to do is we're going to slowly increase the flexibility of all of these individual models, right? We remember when we talked about the idea that if I make something first a linear and then quadratic and so on and so forth, third, fourth, fifth, sixth power, right? I get additional non-linearity characteristics involved in this. We call those flexibility related, right? I now have the ability to make changes to the surface in space such that I can create unique incidences to the clusters of data within that space. So from a classification standpoint, this is a really powerful tool. Yeah, please.
So I know that we can do that with the data in the different folds, but can you also do that while looking at the data from different angles, like you talked about?
For logistic projections?
Yeah.
You can to a certain extent,
Okay.
right? You can to a certain extent. I would say that that's what's really going on here, is looking at the data from different perspectives, taking into consideration a more limited scope of the total of the data space, provides a way of saying, okay, this model relative to this set of sort of angle, this sort of view of the data set, does a really good job at capturing the performance characteristics of the system. So when I say performance characteristics, I'm talking about how this particular feature, this particular predictor, impacts the system, right? If you don't have data points that are really drawing out and really providing us with a good perspective on what is possible, then you're going to have a hard time understanding how to make a model that is robust. Remember, we use the term robust to describe a model that is usable, broad spectrum, right? One that is getting close to or approaching really close to the actual underlying function. Now we know we'll never get the actual underlying function. We're just going to get a really good approximation thereof. So all of this process is really designed to determine what are the qualities, characteristics of a good model, right? Is this system strictly linear? That's the first question we're going to ask. So if we ask the question whether it's linear, and we have all these different versions of the data set, why do I say they're versions of the data set? What happens if I train 4 models on the training data with the same parameters? What's going to be the response to that from what we've done thus far? They're going to be the same. They're all going to be identical, right? They're all going to converge. Models we've used thus far are not stochastic. They don't have probabilistic relationships to the distribution. They don't have random start incidences. In this case, we're dealing with entirely procedural and entirely convergent, procedural convergent models, all right? So probabilistic models may ultimately converge to different solutions depending on the circumstance and how they're initialized. We'll talk about those later on. So if any of you are confused by when I say you get the same model when you train over and over again, I'm talking about linear, I'm talking about multilinear, I'm talking about quadratic equations. When I minimize for MSE, what am I going to do? I'm going to have the global min of the system will eventually be achieved through the iterative process. I will converge to that same global minimization if I train for all the data points. Take some of those out, and what do you end up with? You actually end up with a slightly different model in each case. So the weird part about this is that I get an advantage by using less data. That's the one thing that is really strange here. But because of the fact that the data doesn't have to be held out exclusively for the entire training process, by the fact that each particular individual fold or each particular part of the data set gets to participate both in the training and the testing, then I sort of get it back again in a weird way, right? I'm only offering it up as a sort of like little internal sacrifice in order to try to get the perspective over the whole of the system as it changes. Now, what is going to happen with respect to the distributional characteristics of each of these data sets? The distributions are going to change, right? Take away a fifth of the samples out of any data distribution, and what happens to the mean? What happens to the standard deviation, right? Those values are going to change. The shape of that distribution is going to change. It could widen and flatten out. It could shift over, right? Depending on how that system is weighted, take the right number of pieces off the right side, and you're going to adjust it. But no matter what, when you're sacrificing some data points to this process, you are going to change the underlying distributions. Now, what did we learn about the methodologies we were just learning at classification? Bayesian and logistic regression that utilize probability density function estimates, where do they get a good chunk of the information they use to place the discriminants? The prior, right, that's the ratio of elements within the set, and the density characteristic, which is established by what? The standard deviation, right? The variance, the spread of the data points. So, as a result, we're going to get a different model. So once we change the data, we're going to get a different model. So by each of these models being slightly trained on a slightly different version of the distribution, they're not miles away, all right? They're not over here and over here, right? They are pretty close to one another, small shifts between that system, right? It might be, I don't even know if this one's gonna work. It might be you have one distribution like this, right? That's the core distribution, and the first of the folds might look something like that, right? The second of the folds might look something like this, right? Notice mean, standard deviation, centers. The original center of the system's here, and then the centers of the new system slightly to one side. I'm exaggerating this to a certain extent because usually it is even this extreme. But a slight extent of the relative prior, right? Prior magnitude of the system is going to be cut, typically, somewhat, right? Relative to the total value of the original data points. And there's going to be shifting with respect to the distributions. So by having new distributions and new versions of the data, I'm going to get alternatives from a different, as I said, from a different perspective previously. The interesting part about this is this different perspective is a bit like the multiverse theorem, okay? Right? It's what could have happened had the data set been collected like this, right? Like, Dr. Strange and go there and, then everything's different, okay? You guys have ever heard of a philosopher by the name of Hume? He worked on something called the possible worlds theory. And in his idea, he worked on something called counterfactual conditional. And the counterfactual conditional is very similar to, if you've ever seen the movie The Matrix, right? When he walks into the Oracle's kitchen and she says, don't worry about it, and he knocks the vase off and breaks it, okay? That is the one difference, all right? So the world split into two at that moment in Hume's perspective. You now have one space in which the vase is broken and another space in which the vase was not broken, all right? The thing is that he turns when she says something about it, and that's when he knocks it off. So she says, what's really going to bake your noodle later is, would you have still knocked it off if I hadn't said anything, okay? That's the one counterfactual, that's the one condition that changed everything in that circumstance. These are the one condition that changed everything with respect to the circumstance. I reorder the system and I say, what would it be like if I didn't include these? Okay? What would it be like if I didn't include these? And everybody gets to take a turn at being their own version of the little multiverse that we're establishing here. All right? So we talked about, and I'm going to extend here just a little bit with respect to the idea of classification purposes, because oftentimes I think that there's an overemphasis in utilizing this effect for regression, right? Though regression's boring. So what I say is classification is where k-fold really, shines the most. It can be used for either regression or classification, so it's not preferential there. But there are some aspects to it that are downsides. We'll talk about them in a little bit. One of the advantages we're going to get is going to be, I'm going to show you in the other slides, in the core slides. But notice, each fold here, right, is only a small number. Let's say I've only got 5 samples per fold. I don't have complete symmetry with respect to whether or not red or green class is represented in each fold. Now, why not? Because I can't, right? If I have a 2-class problem and 5 samples, I'm going to have an odd number. Now, if I start dividing up my, all of my herd into white sheep and black sheep, and I'm putting them into their various folds, and I look at it and I say, okay, I want to have an equal number of them in every distribution space. How do you accomplish that? Well, you can't go in and hand pick ones and put them in different spaces. That will cause problems. So what you're going to rely on is just the randomness of selection. So we're going to rely on an understanding of a convergence theorem with respect to the central limit and a weak law at introspection based upon the band of confidence, which is going to say that for any given distribution, we're going to have the equal likelihood to be towards the center or towards the edges for every selection. And thus, if I have a truly random or quasi as random as we can get within digital space number selection, then every fold should have roughly the same distribution as the distribution it's sampling from, as long as it is an equally divided set. So don't worry much about getting imbalanced sets or imbalanced fold characteristics, as long as you're utilizing some procedural methodology for random number generation. Today's random number generation methodologies are very, very good, right? We have, borderline femtosecond generation for SKS keys and the shift encryption. We have cyclone-driven procedural generation. So you're going to get random selection out of most of these cases. It's not perfectly random, but it is random enough. Now, why would I want to keep track of perhaps the seed that I utilize for the randomization? Because I do know that the selection is in fact procedural based upon the seed. So I can reproduce the actual data sets that I'm utilizing in the training process by utilizing that seed. So I can keep track of the data set and reproduce it as well. All right. We're going to talk about the overall procedural process here, but I'm going to hop back over to the slides that are provided by the textbook publisher. I like some of these. This one I do not like. This one's garbage. All right, I'm going to explain to you the reason why. I think most of you can recognize it. What's one of the first things you notice here? It says K roughly equal size parts, K equal 5. Is validation the same size as the rest of them? No. Why do they have to do it this way? Because validation is a bigger word than train. Okay? Here's another problem. Whenever I'm looking at this from the perspective, it's saying 5 roughly equal size parts. Well, yes, it does it for the first fold, but it doesn't describe any of the secondary procedures. It just shows 1 through 5 for the first counts. It also doesn't show validation, the external validation process here. It just shows internal validation. Okay? So it doesn't describe the initial test train split, and then it doesn't actually show you something that makes procedural logical sense. So skip that one and look at the supplemental slide.
So one is what happening to the one validation? What does that define? Can you explain?
We're going to call this the internal. So validation, and the words validation and testing are effectively interchangeable in this textbook. Okay. They are not everywhere. They're not everywhere. Validation typically refers to a data set that is actually accessible by the model,
Okay.
that is not the testing data set, all right? Validation is usually a smaller data set, about 10%, that's pushed at the extended system, that's used for something called early stopping processes in neural networks and other stochastic methodologies, all right? But we're gonna use the term validation to refer to anything that validates the model's performance, right? So it is an external appraisal of the operation of the model. Now, I say external because of the fact that it is obligately not included within the model's training framework. So the argument that's being put here in this slide is that the first fold of the 5 folds is now being used as validation for the model that is made up of the other training. Also, here's a problem. Do I have 4 different training data sets? No. I have one training data set that is now composed of the samples contained within these 4 folds. So what I often would do in this circumstance would be to say, draw you a little bracket down here at the folds and say, this is training, right? It's all of it becomes training, not 4 individual training samples. There is a methodology which we do with that where we train on microcell, but it's not usually used for this purpose. So we're gonna talk about what we're gonna use for notational purposes. And keep in mind, we're gonna use the term cross-validation, and cross-validation means everybody takes turns, all right? This is the across different sets. So cross-validation here is established utilizing K as the index of the number of equivalently sized sets that are constructed based upon the training set. Previously, we've used K as the number of classes, so I think this is a little confusing, and I wish that there could be anything else other than this, but this is how it is dealt with. So once again, just like the idea of how variance is used, it has strange overlap. Here I recognize that we say K is going to be the K as number of folds, not K classes. So when I say CV, right, CV here of K, the K being iterated here is just through all folds, Now, what's happening on this one is fairly simple to look at because we have N, that's the sample number for the global system, and we have N of K, that's however many samples are being kept within the fold. If this is symmetrical, then this ratio here only has to be calculated once, and then we can just look at it with respect to the ratio of MSE, so we can just multiply that value. So MSE of K, why I say MSE of K? That is the mean squared error for a specific model trained on one set of split for the folds. So each version, each rotation, so we're going to rotate who is currently the test set, the validation set, internal validation set, right? We're going to rotate and everybody gets to take a turn. And then as soon as everybody's got to take a turn, we have iterated through all K. So we're going to iterate through all K such that we sum up the mean squared error for all the value sets here relative to the total number of value sets. So this is what? This is an arithmetic mean characteristic with respect to all the performance of all of the models constructed using this cross-validation technique. Now, why am I utilizing a mean approach? Because I'm actually not interested in which individual model is outperforming the others with respect to all of them are slightly crippled, right? All of them are slightly crippled and would likely underperform. What did we say previously? That any data set that has validation reserved from it will likely underperform a data set or a model that is trained on the entirety of the data set. We know why, we recognize why. It's because it has more information. It does better when it gets more info. So, since we have this sort of crippled approach, and every model is equally crippled, it is only the consensus of them, it is only average performance of all the models that give us an indication as to when we're getting an optimization in the level of complexity of the model we're applying it to. So let me pop forward from here. As I said previously, there's nothing new here, and a lot of this stuff is nothing new yet.
I might have missed it, just for clarification. N of K, is that the amount of samples within the fold?
Correct,
Okay.
correct. And N of K is just gonna be what? N divided by K.
Right.
Right, so there's actually another version of this that utilizes the N divided by K over N, rather than NK, right? So it becomes N of N again, but we're gonna go ahead and compute that because we only have to do that once. We just have to say
Right.
N divided by K, what's the ratio on the other side? Guys, can we be quiet in the back row, please?
So
Can I
the
get a
n,
second half to remind you guys being quiet? Yes.
can I, so n of k divided by,
Boys. You wanna go out in the hallway? Text each other if you have to. Yes, sir.
so n of k is the summation, right? And the n is the total number, n?
Yes, N is all samples. That's the sample size of the training set, of
Okay.
the original training set, right?
The total,
That's the total training set,
set,
right?
okay.
So the total training set is everybody, including the internal validations.
Okay.
But I'm gonna evaluate MSE. This MSE here is actually going to come from the internal validation set. It's going to come from the reserved training subset internally. The reason why I say the internal training subset MSE as a better methodology for confirming the operation of the model rather than total average performance is I pulled that data set out so that I could confirm whether or not it was fitting to unseen data. So the fact that it's fitting to unseen data is an indication as to how robust or how versatile that specific model is for the global system. The idea here is that if you've ever heard kind of the expression, you know, good for the goose, good for the gander, it's kind of a situation where if it works for one subset, it should generalize well. So if in fact I learned from this group and it applies to this group over here, it should apply to this group out here, outside the whole system. So those characteristics are based upon the notion that all of these data sets, including these little subsets that we're constructing by setting them aside, by reserving them, those are actually just microcosms. Those are subsamples of the global population sample. As long as they're big enough, then they're fairly representational. If they're representational, they should be interchangeable. If they're not interchangeable, then something's wrong with what? The model. It's not something's wrong with the data, it's something's wrong with the model. So that's the reason why we say everybody should be able to be the training set or the testing set, and everything should work equivalently well if the model is in fact correct. Okay, we're going to talk about another one, and I'm going to use my own slides for this because I have an animation that does a pretty good job of showing this one. It's called Leave One Out Cross-Validation, or LOOCV. Leave One Out cross-validation has a different approach, but I think this is the reason why I mention this is because we're actually going to look, no, right there. What? Wow. Sorry. Leave One Out cross-validation literally says leave one sample out, all right? So this is the special case for k-fold cross-validation where k equals n. You're effectively, everybody gets their own fold, right? So every single sample becomes the evaluation set for a model that's trained on, let's say we have 100 samples in the training set. We're going to train now with 99 and test on 1. And we're going to go round about that process. Everybody gets to be the individual, the odd man out. Now, what's the point of this? What am I getting from it? That wouldn't testing with a singular individual be relatively problematic? Yeah, absolutely. You don't use this to train models. Do not use this to train models. 100%, I want to tell you this. This is not a model evaluation approach. This is a data set evaluation approach. This is in a weird spot.
Oh.
It is more descriptive of the sample that is being held out than it is of the data set that it is being trained with. Let me explain to you what I mean by this. If I have my population here, right? And I just take one individual out of this system, okay? I bring him outside. and then I compare them to the whole
Nice.
world, right? All of the samples. How much has the mean of this sample changed by extracting this singular individual?
Very small.
Very little, okay? What happens if I take one other person over here, right? This guy goes back inside, he's part of the group again. I take another sample over here. What's the difference between the distribution of the first one and the second one? Almost nothing, almost nothing, okay? So when I say that it tells you more about the sample that's on the outside than it does the sample that's on the inside, let's look at it this way. The performance of the individual folds in this case are actually going to be more indicative of telling us whether or not this particular sample is representational or whether it's anecdotal, okay? Don't necessarily use this for outlier rejection, but you can look at it from the perspective of seeing how many goats you have in your herd, all right? This is a goat detection mechanism. Are we gonna have some samples that are not gonna perform well on that standardized level? Absolutely. Well, how many are we going to have, okay? By being able to just quantify that, many times error is acceptable if you can quantify it, right? If you can quantify it. Quantifiable error is acceptable because you can account for it. You know it's there, it's present, you can configure the system to be able to take it into consideration. Yes?
So then does applying both of these together help make a better data set? I mean, a better model, or?
Well, it allows us to evaluate whether or not the model is working.
Because doesn't that help kind of point out like the noise, and then you can kind of,
It will definitely give you, we can definitely calculate something akin to a noise threshold by utilizing leave-one-out cross-validation. But as I said beforehand, oftentimes data science, like in general, data science processing is a bit like a spelunking expedition. You guys know what spelunking is, right? You crawl into the cave underneath the ground. Nobody knows what's back in there, right? You're crawling through the little caves and you're shimmying in there, right? You're doing the hard work. It freaks me out too. But you're doing the hard work, right? You're exploring. You're an explorer. You don't know whether or not there's something in there or not, but you're going to go in there nonetheless. All right? We're data explorers. We're data spelunkers. You can spend a lot of time at it, and if you literally do not know what is possible with respect to the data set, you're always going to keep going. You're always going to think, I could squeeze out that next 0.2%, right? But how hard is the first 20% versus the last 0.2%? Exponentially harder, all right? Exponentially harder. Continuing to improve the performance of a model is just going to get harder and harder and harder to get. Well, for that last couple of tenths of a percent is the hardest chunk of that model. And as I said beforehand, a lot of that's due to variance, okay? So what do I have to do to eliminate the variance characteristic? I have to allow the model to have more flexibility to attempt to capture that variance. So what did we say? How much flexibility does it need, all right? Too much is bad, too little is bad. Too little underperforms, too much overfits. So trying to find that ideal set point, that balance point in the system, right? Where the trade-off between the flexibility that we're provided the model with, in conjunction with the performance that it's been able to obtain, leave-one-out cross-validation effectively provides you with sort of an upper cap of what seems to be possible with respect to this performance. So the average performance of leave-one-out cross-validation is going to be what? It's going to be the individual model trained on effectively all of the data points, except for one in each case, averaged across the entire data set. It's going to say, you're going to be able to get a model that works pretty well, except for these guys over here are really bad. These guys are probably never going to play nice. Okay, and you go, well, how much of a percentage, how much of a ratio are those of the system, right? If they're a standard deviation above the performance of the remainder of the samples, then we're going to say, yeah, there's some outliers here. We're going to look at how much of an outlier there are, and we can even quantify that number at a later point. Okay, so this is the mechanism by which we calculate leave-one-out cross-validation. Notice it's effectively the same as the one we were looking at beforehand, except for the ratio of sample number is 1/n. This is just because of the fact that it is 1/n of the total summation, because it is each individual sample, 1 over the total samples. And there's a weird idea here, a weird element here, the H sub I matrix, or H matrix, which we call the leverage plot. Leverage is a mechanism by which we sort of establish the quality, or relative quality, of a model within a system. So let's say that I have some model, right, that's providing me with this sort of tail behavior here, a polynomial case. Let's say that the density of the actual system looks something like, well, I'm going to draw up here and I'm going to draw the density that this is based off of, right? So the density system comes around here, something like that, right? A couple of distributions, and it's dividing the system. We're going to say that over here towards the edges, the system maybe it drops off pretty quickly. The samples toward the edge of the system. Now I'm going to give you an example here that comes to mind. Remember when we were doing the salary assessments, right? We talked a little bit about salary assessments. What's the likelihood of getting salary, or what's the likelihood of getting values for here's another one. Here's one we've done more of. We only talked about the salary one initially. What we've done more of is the credit evaluations, right? So people with really high numbers were not included in that set. People past like $2,500 in debt were not included because there weren't a lot of people that had that much debt within the system. So when I model it, when I get to the end of this system, sorry, that's not very smooth. When I get to the end of this system, what do I have? Well, I have essentially an extrapolation, because the function keeps going, right? But I actually have something that can be plotted here with respect to what we call leverage. This is effectively the localized confidence interval of that model. Because as the density goes down in any specific direction towards the edges, toward the extrema of the model, your confidence in your appraisal, your confidence in your predictive capacity of the model is going to go down. Why? Because there are fewer samples in that space, there's less information to base your conjectures on. So the fewer samples, the lower the density relative to the unit space, the less confident that particular model becomes. The H matrix is effectively a mechanism for associating what we call leverage. Leverage is related to the moment of the system, which is a quantitative assessment from the mean characteristics. So we utilize the residual square, standard error, over this, which is effectively the diagonal of a matrix, over each individual sample or each individual element to every other individual model of the system. So one versus the rest, as each sample becomes the testing set for the training set, the remainder training set. We don't calculate this by hand, it's too big, all right? I'm never gonna ask you to calculate it by hand. However, you guys are gonna do some of it whenever we do the lab for chapter 5, which is lab 4. I'm not sure whether or not we're gonna do that as an individual lab or if we're gonna do it in combination. But I'm gonna probably do a shorter version of it with just the cross-validation as prep. So today I think I'm gonna put that out, and I'm gonna put out also the review worksheet for you guys. I've been having a little bit of difficulty with just kind of getting things to post ready, but yes.
Are we gonna be expected on the exam to do any like hand calculations of stuff?
I hardly do anything even remotely related to hand calculation, but I will say that you might be asked to do stuff like simple ratios, okay? Simple ratios, and just to be able to count, okay?
Oh man.
If you can't count, then we need to talk, okay?
That's it.
So, that's it, I'm done now, can't do it. So,
That's most of my errors is subtracting
one of the
one
things
and
that I
adding
often
one.
will throw in there for you guys is like how, like the calculation and determination of the confusion matrix, right? If you look at a graph, right, here's the graph with the actual data points on it, here's the model version of it, right, here's the testing, and here's the training version, okay? And then develop me the confusion matrices for the test and train versions, and then maybe do some comparison between them, right? But it's gonna only be for like tens of samples, so it's not gonna be hundreds or anything stupid. So you're just gonna have to go through and count, circle the ones that are on the wrong side of the boundary, and determine the values. All right, so as I said beforehand, leave one out cross-validation does not shake the data up at all. Matter of fact, it only slightly jostles it, right? It may even just nudge it. a little bit, because one sample is just not enough to make a difference. So it doesn't really mean much, because effectively the models generated from each fold are effectively highly correlated, hence their averages can have relatively high variance with respect to the sample that was left out. It is in fact the high variance of the samples that are left out that is the target of this model. I don't know what the authors of this textbook think this is for. I've read the textbook, I've watched their videos, and I'm telling you, they just seem like they just totally deny that this has any use, all right? Its use is identifying the difference between individual samples versus the consensus. As I said beforehand, if you have a sample that has high variance, then you're going to be able to identify the total number of samples that have high variance or high error relative to the held out sample. That is likely going to mean that that held out sample is not representative, because guess what? There isn't much difference between the models themselves fold to fold. However, there is a lot of potential difference between the sample relative to the remainder samples within the set. One of these things is not like the other. One of these things just doesn't belong, okay? So that's the characteristic we're bringing to play. A better choice here is a K of 5 or 10 with respect to the K-fold model. Between 5 and 10, you can go past 10. There are very few uses for it. Partially this has to do with the fact that ratios of scale for models that start to get into like 1/8 or 1/16 of the total data set is not sufficient to capture the overall variance in the system. So it's very likely that you'll get a strange distribution in the testing, yes.
So how much does the size of the actual data set play a role in choosing 5 or 10? Or is that just kind of?
It's a gut instinct. This is the part where we go.
Subjective.
It is a little subjective, okay? I tend to push to 5 to begin with, and then I say, well, 10 if it's really big, okay? That's where I say small data sets, the smaller data set, the smaller the K number. It makes sense in that way, because guess what? We're capturing more samples whenever we are still having, let's say you have 5,000 samples, all right? That means that you have 1,000 samples per fold, right? Well, that's pretty big, that's a lot, okay? We could go down to 10, we could go down to 500 samples per fold, and we go, that's good, right? That's still probably big enough. Now, why would going to more folds be better? Well, it really depends on the granularity you want to get into, right? You want to know whether or not a third or 3.5 or fourth dimensional model is going to do a better job here, all right? So what we're actually talking about here is going to be described in this slide. And this is probably going to effectively be where we stop for the moment. But notice what's going on with this graph. We have MSE, right, mean squared error, and this is, of course, the individual performance MSE, all right? So this isn't the mean performance MSE. So mean performance one that I gave you, the sigma notation version of the summate for all of the models, right, the average performance. This is this before the average performance has been applied, all right? So leave one out cross-validation just has a singular value for each of the model performances, because it is summational. Has to be. You can't really do it for 100 or 1,000 samples. The graph is meaningless. So what we're doing is we're comparing the average leave one out cross-validation to 10 individual folds within the same data set. Now, leave one out cross-validation says that the maximum increase in relative performance occurred by taking the model from a strictly linear to a quadratic expression, okay? So by going, this is saying degree of polynomial, not flexibility of the model, all right? There's two different ways of saying this. Degree of polynomial goes from 1 degree to 2 degree, all right? So it is a second degree poly. So over here, we're gonna compare second degree poly. Yep, we say, yes, it agrees. So the leave one out agrees with the K-fold cross-validation, the 10-fold cross-validation over there, that we're getting most of our performance increased by adding a nonlinearity, right? But what happens afterwards? We're making our model more and more flexible. So we go from a piece of paper, right, This is our plane that we're working with. We go from being able to add a curvature to it, right? This is what's happening on that end of the system to this, okay? Right? Here's the model. Maximum flexibility, all right? It's just super floppy, all right? It goes wherever the data goes. Too much, it's going to overfit. So by having that consideration, as we say, where do we stop in between? What's a good trade-off? My answer here is probably 2, right? Because that's the maximum return on investment. It seems like you're getting maybe a little bit up in here by the time you get to 6 or so, but let's go over and look at what happens with the actual points over here. So the beauty of PDF, I can actually zoom in on this, right? Can I get much out of this? Not on average, I'm not. However, if I just did this just for the training data, right? Just for the training data, what would happen? I would have one line to determine. Now I have multiple lines to determine with, right? Multiple different versions of the data set to compare together how their performance changes relative to the change in flexibility of the model. Now I go, oh, not only am I making the appraisal of the increase in flexibility based upon the data set, now I'm making it based upon possible worlds in which this data set could have slightly different configurations. If the data set has different configurations, and in fact they are sourced from the same distribution, then all models should perform equally well on the model that is ideally configured for that system. So as the system converges, what's going to happen to all of these different data set systems? As the best model is going to have relatively consistent performance within the system. That is right here at 2, right? What happens afterwards? We have a divergence again. Notice that divergence. What is that divergence indicating? That divergence is indicating that as I increase the polynomial in the system, this performance is less stable. It becomes more what? Data set dependent. You guys remember I used that term to describe the concept of overfitting? This is the idea that the data set dependence is some models, some specific data sets with respect to the fold system will work better as the flexibility is increased, but that's only because the Shyamalan movies aren't in there, okay? That's the only consideration, right? So for any of you who don't get my stupid joke, watch a Shyamalan movie, you'll understand. It's like, it's totally different than anything else. There's a twist at the end, right? So here's the twist at the end. We don't utilize leave one out cross-validation for much of anything, but you are going to utilize leave one out cross-validation for creating your understanding of flexibility, but you're not actually going to train your model with this. Why? Which one do I pick? Which one do I pick? I just established the flexibility of the model, and then I train that model on the whole data set. Train the model on the whole data set. This is just a coefficient parameter estimation methodology. This is just to determine what the ideal flexibility of the model will be. Now we can go back and we can use the entire training set to train at a second-degree polynomial and be pretty confident that the relative performance of that model is going to be the best out of all of the parameters we could have selected for it, because we knew what happened when we continued increasing the flexibility. So now we have a better understanding of all of this sort of quantum reality, quantum probability for divergent data set selection within the system. So K-fold methodology is reserved for data set and data set system evaluation, such that it provides us with a better understanding of how complex we can get it, right? To what degree it will likely be accurate relative to some specific degree of flexibility for polynomial fits. Okay, thank you very much. Appreciate it all. See you guys on Friday. I will let you know if anything changes on that. I might have something that I have to do on Friday morning. If I do, I will actually put out a video for you guys this week, because I want to make sure we get through the material.
So the next Friday, the midterm will be on chapter 2, 3, and 4.
No, chapter
2 to 5. 2 to 5.
We didn't cover one specifically, but we did do a lecture. We did an introductory lecture and an overview That's chapter one.
Oh, you have actual,
From chapter 2 to 5, okay.
come on, pack your shit, let's go.
I might actually stop.
I gotta get to work.
Bootstrap on the midterm.
I gotta turn on my
We'll have the bootstrap done probably on Friday or Monday. Okay, that's the only other thing we're gonna get to is chapter five.
It's not
Chapter
working.
five is much.
Did it die? It might have died.
I will not be here on Friday. I had a drill. Do I need to email you the?
Oh, come on.
I'll pretty much take any time that you're not here as there's a good reason for it.
Okay.
Thank you.
I guess my battery ran out. I guess I'm stopping by one stop today.
What battery? What's this?
What's what? This is my work computer.
For the stuff that he does, he can pass on the DSS.
Taking an exam a week ahead requires you to have.
One-way communication is the only thing that's authorized.
Okay, bye. Have a nice day.
Yeah, you too.
That's, I've been explicitly told by the department, I'm not allowed to. Alright, so when I originally said I wanted to do it Thursday, why is because I have another class section. So since my TA is able to, he could theoretically proctor an exam. Problem is that so you're gonna be leaving when? You're gonna be leaving next month.
So Monday or Tuesday, it's fine.
Let me see if I can figure out a way to do Tuesday. That would be admissible, but that is, like I said, that's still pretty early, and since I do have another class section that I would be offering, it's kind of difficult to say for a single day. If there's travel involved, so you just an in-person interview?
Yes,
Where are you traveling to?
Washington.
All right. Now, let me see what I can do. I think you can work it out for Tuesday. I just don't want to do an entire week early. That's, like I said, I've gotten called on it before. Last year I had students who tried to take the final early, and they basically told me that, we're not allowed to give early finals anymore. So I just said, you know what, anything now on 1 week is maximum if you have a valid excuse. So thank you for following up. Thank you for coming in and talking to me about it. I'm glad to be able to do that in person. I will try my best to try to find a time for you on Tuesday. Is there any reservation for time for you on Tuesday?
On Tuesday, I have another exam from 4 to 5, so
All right, so we'll do it earlier in the morning. Can you be on campus by 11?
great.
Okay, all right, so 11, let's do 11:30 actually, and we'll do 11:30 to 12, whatever, 12:50 or 12:40. It's whenever I actually have to leave, so. Yes, in my office, 4:50 a.m. So, I just, it's, you see the big phones on the 4th floor, right? Turn right, my office is all the way in the corner. Okay, yeah, okay, good, okay. Yeah, thank you very much. I appreciate you letting me know. We'll do it Tuesday. Take care of it. All right, all right. Good luck to you on the interview. I know, I'm sure it's stressful.
Yeah.
So, but who are you interviewing with?
Yeah, digital reach agency.
Oh, okay, wow. So government offices. Wow, that's it. Well, good luck. Awesome. Okay, talk to you later on. Sounds good. Let me know. Make sure to confirm with me on like Monday and follow up by email, and I'll go ahead and set an appointment on the calendar to make sure we've got everything. Okay. Good luck. All right. Thank you. Yes, I was. I mentioned today. I've actually not. I've been feeling well. The last couple of days, I just have not had a lot of energy, and so I'm just kind of behind schedule on a couple of things. I do have some review material, and I intend to post it. I was going to do it yesterday, but I had to make some modifications to it, and I got the modifications done, and then I just didn't get the posting finished. So a lot of times that seems to happen for me. I just hate Canvas because I have to post for 4 sections for this one class, so it's just a huge pain in the butt. But that's not on you. I will make sure I give you as much as I can in advance, You should have all my supplemental slides, and then I will do a review for you
So,
guys before the actual exam day. I'll probably do that on Konata, that way you can watch it separately, so. Yeah, you haven't missed anything yet, I'll get you some stuff here soon. Okay, yeah, thank you, good luck to you. You guys have more talking. Give me one second, to try. What's that?
So, for lab 3, I tried using the IS data set, and what happened was, I thought I could simply use SQL and then bricks for the classification, but then I ended up having a complete separation, so it was either 0 or 1.
Yeah,
I think I'll need a little
I
more.
think you might have reprojected that a little bit. Did you
Yeah,
submit
so-
something already?
No, yeah, I used a similar data set that you used in the lab. But
You did submit something on,
Yeah.
okay, but you wanna update it?
Not update,
Oh.
I want to understand that a little more, so.
Okay.
What exactly was the problem there when I used SQL and then with, was it because there was like very minimal, number of data points, falling into each other?
No, there should be there's 150 data points in
Yeah.
Fisher Iris, so there's
For-
50 points per class.
For
Sepal length to sepal width is well separated for Setosa, but not well separated for Virginica and versicolor. It needs to be reprojected. So with a strictly logistic regression, you're gonna have good separability for operations, but here's the problem. Were you using logistic regression for a 3-class problem?
No,
You were using LDA?
for the logistic regression, I ended up omitting all the, Setosa, these things, the data
Okay,
points.
you eliminated Setosa.
Yeah.
Okay, so
So
you're just
then-
separating Virginica and versicolor.
Yeah. For the class.
And you ended up with good performance for logistic there, or no?
I ended up with a warning stating there was complete separation, 0-1 probability. I don't remember exactly. I think I had a picture.
That seems like potentially a labeling error. I think it's probably a labeling problem because they are not fully separable in that
Yeah,
actual
I
space.
had
Did you include it in your notes, okay, send me what you have, what your stuff is. If you shifted gears and you'd like a response to something that you ran into, fine. In the future, I don't require you to actually have it, not everything has to work, right? I just expect you to make a reasonable attempt and then try to figure out why it didn't, right? But if you did shift over to something that was workable, that's good. That's usually means that you understood what was going on and that you shifted away from it. But at the same time, I do want to know what you ran into so we can figure out how to fix it. So send me an email or make a comment on your grading. And I usually tell Rowan to shoot me anything anybody has comments of grading, but just email me directly. I'd like to see what your code was, and I'd like to see what it's out there.
Or maybe I ended up excluding one of the versicolor and Veronica kinds, so.
It's possible that you might have ended up excluding an entire class.
Yeah.
That's possible. Like if you get down to just a 1-class problem, that would be very separable.
Okay.
You might have excluded too
Yeah,
many.
yeah, yeah.
You might have actually done the inverse of what you thought you were doing. You might have just made just Setosa and not Virginica
Okay.
versicolor.
Yeah.
Look at see whether or not your which labeling, so
Right.
whether it's in the appropriate binning, right? So we put it in the bracket, you
Yeah.
got like a range value. Oftentimes it enumerates from 0, not from 1 like Python. So you might have been eliminating 1 and 2, and then thinking you're 1 and 2 of 3, right? You see what I'm saying?
Yeah,
Okay.
but then after I created the test data set, I mean training data set, it had 100 data points, not 50. So
That should be right. However, if it was Setosa versus Virginica or versicolor, they are 100% stackable, and logistic regression would not work.
Yeah.
It will warn you. It will warn you if separability is too high, because if it says that there are NSC methodology, right? So we're looking at it from the perspective of saying it's attempting to minimize between class spread operability, not the within class spread and between class spread like LDA, but it's within class spread operability. So it's mean to mean. Well, if mean to mean is separable by more than 1 point, it's non-singular, and it will tell you that it's fully separable and you can't do it. So at least it stops you from trying and realizing.
I think I ended up.
I think you might have separated Setosa, where you need only Virginica and versicolor, the only two that are gonna work with logistic regression.
Yeah.
So, Like, it looks like you noted what you were running into. It looks like you saw and found out what the problem was.
Yeah.
And I think all of these extra problems that people are running into are actually helping them understand the concepts better.
Yeah, initially I had like, everything was going above my head, but yeah.
And then you start messing with it and you go, oh, now I actually know what this
Yeah.
means because I can see it on a graph. Yeah, so I think the practical aspects of this class, I've been rewriting all the labs. I've been adding to them. Where you do the lab and then you do something else yourself, that's all new this year. So I only at one time last year did I expect people to do it on their own, that was in the final. I think that was a terrible idea. So, because people got to the end and they were like, I don't know how to do any of this crap, I'm out of time. And it's like, no, you'll be able to just basically take your code from your previous labs and finish the final this semester. So things will be pretty easy toward the end of the year. So, Cheyenne, what did you, thank you.
Okay, thank you.
So I just missed it one of the part I didn't know. So I saw the John.
Yes.
So I didn't do the the logistic regression, that is you explained me the default of the credit card.
Yeah.
Like I didn't do that one.
You didn't do logistic?
I did the logistic. I didn't do the graph. That's what I'm saying.
Oh, okay.
I did the everything, and I also plotted.
Did you put up your outputs from the system?
Yeah, yes.
Oh, you're fine, you're fine.
Everything.
I just wanted people to try to use the logistic plot, because there's actually a function in mass that has a logistic plot. So somebody asked me about it, one of the students asked me about why, like how to do the regression plot, and I told her, hey, come by my office and everything else, and then I didn't hear from her anymore after last week, so she must have figured it out. And
So another thing I did, I also
if you miss something in the lab, don't worry about it, usually it's not a big deal.
So I also did something in the lab, like extra code.
Okay.
The thing is, I don't know in the logistic regression from the book I followed, I didn't know it's testing or training data is different. I did it separately, making more like taking the variables for testing, variables for 30 to 40, 70 to 30. Again, in a logistic regression, I did it again to understand how does it working or not, and I put it on the lab. So I got accuracy. It also shows me the accuracy I got it. It shows
65, 67%.
74.
Oh, wow, that's pretty good.
So
Usually 60s is about the max for most of those data sets. 'Cause
so,
they're really
but it was good. But I'm still confused some of the part. Like when I use the com, like I forgot what the com is. So that's the 0 and 1. That's the way I want to understand. Like the directions, it's up and down.
Mhm.
Up and down direction. What we represent is 0 and 1.
Yeah.
So I'm trying to implement that.
Why up and down was presented in the previous one is simply because of that those are the data labels,
Label.
right? You can use anything for a label as long as the appropriate level is provided,
Yeah.
right? So as long as you've converted the value into categorical, right? By the process as factor, utilizing the term as factor.
So
I use the term, say, convert to categorical because I'm used to using that Python terminology.
okay.
So in Python, you actually use the categorical conversion.
So
But correlation, what you're talking about is called correlation. Right,
correlation.
so that's the correlation coefficient calculation.
So I tried to, but I got them messed it up. There's two data. I think there is. If it was there,
Uh-huh.
it will be very valuable. It's a class data. It's
Yes.
a classroom data of the normal. So I say if there is the gender, then it will help me how to understand the gender equality is there or not. And I also included if the year is included, then I can understand how the year is provided. So these are the two data. If it was there, then it will be more better, I say, because those two data can help me out to understand more the two features. Like
Two features will definitely be able to provide you with more
More
information,
information.
for sure. But the question is whether or not they are useful and separable, whether there's a degree of separability with respect to those features
yes,
as projected. So add a feature in that is not well separable, and it will actually cause the model's performance to drop.
drop. Yes.
Yeah, so that's what you're thinking, that it should inform you better, but in reality, it does exactly the opposite. It confuses the problem. So what you're recognizing is something that I talk to people in industry about a lot, and that is they think that more data and more dimensions is better. and say, well, maybe from sort of a socialistic slash idealistic perspective, like I'm gonna take every factor into consideration. But there isn't actually a way to do that. You do have to sort of hold certain things fixed while moving other things. So for instance, a lot of people have elevated CO2 levels beyond, like, they're like, CO2 levels are the worst thing ever, right? And then they don't realize that things like fertilizer production generate CO2.
Yeah.
It's not substantial, but it's something. But if you regulate fertilizer production to a point to where what happens? You say, oh, I'm gonna regulate, you're in zero CO2 output. Well, in order to have zero CO2 output, I'm gonna have to make my fertilizer prices stupid expensive because I'm gonna have to add all this stuff to my machinery. What happens then? Fertilizer price gets passed on to the farmer. Farmer passes it on to the wholesaler. Wholesaler passes on to the customer. Customer ends up with less affordable food. So we say, oh, global warming is gonna end everything. And it's like, yeah, but your solution is gonna end everything too, right?
Yeah.
Oftentimes your diagnosis can be correct and your prescription can be entirely wrong.
Wrong, yes,
okay?
it happens.
So attempting to incorporate something like decision-making purposes and hiring practices, and then doing something like gender equality biases at the same time, you say, I can't do both, right? I can't control for both systems simultaneously. It's too much, it's too interconnected. And things like social biases and other characteristics change over time, right? So you're saying that I want a model that categorizes something that is in fact temporal. You need an entirely different model. It's not just a procedural classification model. Now it's a classification model that changes with respect to time, right? Now you actually need a differential model. So you're gonna have one model that predicts a regression, and then you're gonna have another model that predicts the classification, and it's gonna do a component score. It's gonna multiply the regression times the incidence classification score. It's gonna give you a different emphasis. One is a regression, a temporal characteristic, right? The change in value over time. And then the other one is a probability of higher rating for incidence at that level. You need multiple characteristics of the model, multiple levels. We haven't had the tool for that yet, but that's probably gonna be something like a decision tree or a support vector machine. Or like LBT model or TDNN model, time delayed neural network, can be run alongside. You get temporal characteristics alongside quantitative characteristics. So quantitative characteristics can be maintained by attention. So if you've dealt with those metrics before, in a small way, attention is figuring out what the most significant factors are with respect to time.
Oh,
right?
yeah.
So your attention can change, your focus can change over time, right?
Yeah, the time.
So
where-
when I got done with him, I shifted my focus to you, right?
Yeah.
So there was an epochic relationship. I worked with him and then I got to you, right? I changed focus. What was most important at the time changed, right? So that's the idea of attention models change over time to make what is most important at that time can change. So since it's not the same features are not equally relevant throughout the entirety of the system, saying these features were relevant then, these features are relevant now, these features are relevant now, we have to be able to adjust which features are the most important to the decision-making process over time as well.
So this is like, I've done a model on ARIMA.
Mm-hmm.
So this is ARIMAX or ARIMA, I think. So did you hear about that?
Yeah, RE is Minimax, RE is, yeah,
So
sure, it's a
we did for the
competition basis.
competition basis.
Yeah.
We did the same for the crops, but according to the price, the
Mhm.
price is related to the time.
Correct,
So the price is when the price is up, then the price is up.
yeah,
When at the time is price is up. So we calculate and predict which is going to be the next 5 years or 2 years, what the price of the rice will be.
Correct.
So yeah, but we did it.
That is a very, very big calculation that has a lot of external factors in place. I think that's the
we
reason why I
did
say.
it very small, to be honest. Like
Yeah.
we didn't tweak anything, but it needs to be more precise and tweaked it inside.
Well, I think the biggest part of it is oftentimes you can have an overly simplistic view of something that is in fact highly multivariate. But also you can have something that is you have a data system that's highly multivariate where only a very few factors are actually playing the biggest role in that system. We're gonna talk about that in the next chapter, which is regarding to feature selection, right? So feature extraction, feature selection, and feature projections are what we're gonna work on. And we're gonna be able to determine who's in and who's out with regard to features. And you can actually change those over time. You can choose which features are in which places using something called a generalized additive model, or a GAN. You can utilize different subsets of the features to train different models and then add them all together to create a model that is, for different regions, has different performance. So it's really pretty cool. We talk about piecewise functions, in which you actually have multiple models that describe one relationship, so something changes over time. You have like I talked about with the COVID, were you there for, you were there for the talk when he was talking about utilizing the Poisson distributions to model the decay COVID?
Decay COVID,
Yeah, the spikes and then
yeah.
the drop-offs. I thought that was a massive oversimplification for personally.
Yeah,
A couple weeks ago.
couple weeks ago,
Friday.
yeah, we were there. So
The reason why I say it's piecewise is because he's treating the drop-off as one function, he's treating the exponential increase as another function.
yeah,
So he's treating the exponential increase and exponential decay as two different functions, which makes sense, because one is a propagation standpoint and the other one is a secondary infection standpoint. How many people get infected by the residual of the spike in the first infection? So it's as I said, it's an oversimplification to try to reduce it down to a single factor exponential decay system. So I don't know, I thought he wasn't taking into consideration a lot of other factors. Well, a lot of people might disagree because they go, well, if it's a system that can be modeled by a probability distribution, then it has to be, either geometric or log likelihood or exponential probability distribution, because that's the only density characteristics that we really have. And I'm like, yeah, but sometimes it's smaller distributions that are aggregated together, right? We tend to look at the whole system. This is all infections everywhere in the world. And it's like, okay, well, that's maybe a little bit too much to use the same model for all of it. Yeah, like we probably need to look at it as the integration of many other smaller models along the way. But the problem is that becomes, how do you know who to break it up with? Do you do it based upon region, based upon city, based upon age group, based upon population, based upon
there's so
demographic?
many reasons.
There's so many underlying factors you can attempt to model, and each one is correct in its own right.
Yeah, like they say,
Yeah.
every model is a bad model, but some of them are useful.
Some of them are useful, exactly. Yeah.
So I have
You like that quote, huh?
yeah, I like that one because now I understand everything is a bad model and I have to make
Just
use
some
of
those-
it.
Yeah, it doesn't have to be a good model to be usable.
It's usable. So that's how it goes through now. So one thing I didn't last, the classification. So
Yeah.
that is the thing. You told me there's a big cat and small cat. Okay, the big cat is the lion, tigers and stuff.
Yeah.
And the small cat. Those have the same features. But
Similar
they're-
features.
Some of the features,
Yeah.
they have claws, they have
Yeah.
furs,
Sure.
they have nose and ears, everything
Yeah.
gets the features.
Yep.
They both have different sizes.
Do you know how most image processing systems separate them?
By linear regression?
No.
So one of
No.
I discussed with
Linear regression, oh my gosh, that would not work. It's not nearly complex enough. Not nearly
Okay.
complex enough. That's like, no, it's like a 50th order poly system. I mean, it really requires significant, whenever you have overlap like that, how do you create good separability? You find something else to decide the space with. You recognize it, but you don't recognize it. Where do you most commonly see cats, felines? Felis domesticus. Where do you see them? Inside houses, right?
inside houses,
Yeah,
yeah.
where do you see lions? Out in the
Outside.
savannah.
In the forest.
Yeah, in the savannah.
Yeah.
Well, I mean, I don't know. So you got jaguars and stuff where you guys
Yeah.
are at. Is it jaguars? Or
No,
you guys
no.
have
In
pumas?
Bangladesh we have tiger.
Tiger. Oh, yeah, tiger. Okay, yeah. They say they have leopards and pumas and stuff like that in northern India too. But they got tigers as well. So you have tiger, right? So you see tiger in the jungle, right? You see cat in the house. Okay, how do you separate those two things? Yes, they have similar features, but the images don't. The images actually have a degree of separability, but what is the degree of separability? It's the background.
Ah, that's the simplest one.
Context.
Context. The
Yes.
environment.
Yes, the environment.
The environment.
Yeah, most models that you come across today, their separability is based upon the context the environment is in.
So
You want to know one that really will blow your mind? Show a picture of a human individual in a domestic kitchen, inside of a kitchen space, right? And let's say that that person is facing away from the camera. And you ask the camera, is this a man or a woman? It's going to say it's a woman, right?
because most
Because most of the time pictures are of women in kitchens, right? But show an industrial kitchen, right, with a chef hat on, and it's gonna say it's a man, because it's more common that it's a man in the industrial kitchens, right? So it's still a kitchen, and the system can identify that it's a kitchen, but one kitchen is the industrial kitchen, and the other is a domestic kitchen. Guess what? All of the data it was programmed with, all of the examples it was given it was all women in the home kitchens and all men in the industrial kitchens. So it says the populations are indicative of the environment. I will make my determination about what's likely to happen based upon the environment. Guess what? We do it all the time. Humans make almost all of our decisions based upon context. That's the reason why I said attention cues, what is most important or most significant relative to the consideration, is what? I don't want to just look and say it's a kitchen. I want to know if there's a person in the kitchen, and I want to determine what their gender is. So now I have to isolate the person and attempt to describe some features from them relative to most of the image being kitchen, right?
Yeah.
90% kitchen
Yeah.
and 10% human. Okay, how do I determine what the gender of the human is based upon that? Only the context of what I've shown you beforehand.
Yeah.
You're a little boy that lives in a box, right? And I poke little pictures through there and you look at them, right? That's the best example that I have of AI right now. AI is
It's a baby.
it's viewing the world as, you know, it's shadow puppetry, right? It sees the shadow that's following the wall. It doesn't see the actual 3D object. It sees the shadow that's been projected on the wall. We're the ones projecting the shadow on the wall.
Yeah, you told, like, we are projecting, like this projecting is projecting it, and we are
Yeah.
projecting the shadows.
Yeah.
So based on your, as you have explained, it's like you have, the kitchen, the constant of the kitchen.
Yeah.
Kitchen is the classification.
Kitchen would be a classification.
Yeah. So,
You remember,
The data set
you
is
remember
never-
you can use categorical inputs as inputs for other classifications, right? So if I take an image and I say, here the background of this image is kitchen, and I feed that into another section of the model, and I say, tell me what this person's gender, given that this is a kitchen, right? Now what happens? Now you have the Bayesian probability again, right? It's likelihood gender female given kitchen. What happens? Well, what's the density? What's P?
likelihood gender kitchen.
So it's P of gender female
P of
given kitchen,
kitchen.
right? Do you see what I'm saying? I've given you that it's a kitchen.
Yeah.
What's the likelihood that this individual is female gender given kitchen? What's the likelihood of the gender male? What's the likelihood of gender female given that it's in a kitchen? Do you see what I'm saying by that?
Yeah. What's the likelihood of being female in the kitchen? What's the likelihood of male in the kitchen?
Yes.
So
So if I already figured out that it's a kitchen,
Kitchen.
right, I provided you with that information,
if it's a female,
then what you're gonna go do look like, you're gonna go and look at all of the males and all the females in kitchens. You've constrained the search area, right? Previously it was everything, now it's just kitchens.
Kitchens.
If you don't constrain the search area, what ends up happening? There's too many possibilities. Almost everything about models, deep learning models and all the stuff that's coming out today is all about bringing down the search area to a reasonable size. And how it's done is based upon context.
Okay.
What's around it matters to what's inside of it.
Okay. So that's the classification. It's not the data classified, but can we say the data can be classified? Like the cats have like the kitchen.
Mm-hmm.
Kitchen of male have different data,
Mm-hmm.
and the kitchen of female has the different data.
Mm-hmm.
There is a two data,
Mm-hmm.
but based on the classification of the kitchen context, we can say like that.
Why are we as humans able to do it?
Okay. Why?
That's a big question. I want you to think about that. I want you to look at it and say, why can I tell the difference? And it can't.
It can. It's a machine. The machine can.
You're a machine too.
Yeah,
You're
we're
a
all.
machine too.
Yeah.
You've learned based upon contextual information, but let me tell you something that you have that the machine doesn't. You have an imagination.
Yeah.
Meaning that you're constantly running back scenarios in your head and changing stuff out and doing the possible worlds analysis that I was talking about today, whether you knock the base off or not situation, your brain is constantly doing that.
Yeah.
So in fact, you have more experiences than you have real life experiences. So you have real life experiences and then you have simulated experiences. You are able to simulate within the context of the natural world, physics and procedural design, in a way that computers can't do. They can't imagine something different. So they're stuck entirely with what they have. They can't imagine what it would be like or what it would look like if it was a woman versus a man in that situation. And thus, they're not looking for other things involved with it. But here's the other consideration. How good would you be if you only had one picture? That's the difference. Humans are actually not a lot better at determining, say, gender or something like that from a single frame of an image.
Yeah.
We do a lot of what we do is based upon movement, right? Change in the procedures of the system, right? I challenge you to say this. One, I challenge you to be able to determine the gender of an individual at a distance without them walking.
No.
You can't, and the reason why, how do you tell the difference between genders
Because
when they
they-
walk? Do you know why? Do you know why you can tell the difference between men and women walking?
Because they have different patterns of walking.
Yeah. Why?
Because of the body structure.
Their bone structure is different, the hip structure of female is different. So they actually walk different, their gait is different. So we classify walks in our brain since we were children to be able to determine the walk of a female versus a male. We don't pattern it, we don't make ourselves pattern based upon what we see. We walk how we walk how we learn to walk, because we didn't walk with conscious understanding of gender at the time. Nobody at 2 years old, when they're learning to walk, has a conscious construct of gender, whether they're their own or other. But throughout our lives, we recognize the otherness of gender by being able to recognize formational constructs in that system.
The bones, and also I believe the bones also helps us to like you're a male and you're a female.
Oh yeah, for sure. I mean, bone structure matters.
Right.
Upper body density,
Yes.
hair structure, facial structure matters too, right? But facial structure is a little amorphous. I've done work on both. I've done work on gait analysis. I've done work on processing to be able to determine gender and individual identification by watching someone's walk in a video. And I've done work on facial feature extraction for
So you have done image
recognition.
processing like most of the time, I think.
For almost 7 years, yes, for my PhD. And I didn't work just on my own projects, I worked on other projects. The one I'm talking about, the gender analysis, was with Dr. Gita Ratani. So she's down at Texas Tech, she was at Wichita State for a while. And then gait analysis work I did with Spanina Druki, and then, I think she got